Peace. Okay. Let's check the sound. We just wanted to. Right. Before, there was this idea of a light mill that is a computer, that you can shine light on something and get it to move. So if you have missing bits out of this Ferris wheel, you can get it to move some of the time when there's a missing bit that the light should be hitting on. So with one continuous stream of light, you can get this thing to sometimes spin and sometimes not spin. So with one continuous stream of light, you can get a light mill to spin and not spin if there's something missing, but also perhaps to drive another thing which is continuously spinning. And then you can make a sort of computer that just is powered by one continuous stream of light. There's always ways to make the little carriages on your Ferris wheel reflect out light to maybe another light mill, which then spins a little bit, and you can make a really complex computer out of just one beam of light and several things that it can interact with to make them spin. Now, we're particularly interested in actually a linear case of this, where just imagine I've got well, we started out with if I've got maybe a glass and it's filled up with water and I wobble it, I knock it so that it's wobbling from side to side, then if I shot a laser over the top, there's a certain height of laser that this wobbling glass is only going to unobstruct when the glass is sitting at rest. And you'll be able to maybe measure from the bottom too that something is touching both of these points at the same time, so the glass must be sitting down. I want just one of these types of computers that tells me is the thing obstructed or not obstructed, um, where everything is placed one plank away from each other. So I've got the minimal distance that you can measure light between, and then there's the thing that maybe obstructs or doesn't obstruct, and then there's the thing that you're looking for. First comment on this is that whilst our target to see what we're, to see if we can see it is 2 planks away, that means that it takes 2 light seconds for, two of the briefest interval to be able to verify that it's unobstructed, but only one interval to verify that it's obstructed, which is strange. When we shrink this all down to the minimal possible scale, we find that, well, we've never broken the speed of light really because the thing was 2 planks away, and to test took 2 planks. It took the time it takes to get to the first one, and then the time it gets to come back. Okay, if the thing that we're checking is further and further out, that the possible obstruction is at the first plank after where we're watching from, but the thing that we're checking is 2 planks behind that, then it's going to take 3 plank moments to verify, or for a complete message. And it's going to work out that the square of the distance is how long the extra delay time is. And so if you were working at the square of the speed of light, it would linearize, if you can do that. What does it represent to have something very close to us being the checky thing compared to the thing that's being checked? Well, it's very similar to having a very narrow idea of everything to do with angles. That if I'm trying to measure something all the way over there with something that's really close here, it's going to give me the same kind of information no matter where that was related around me. It's going to matter very little. The thing we're particularly interested in here is that if there is an obstruction and there's something obstructing light, then there's something in the way, and if there isn't, there isn't. And so we have a good representation of, like, well, in one case, time continues on, everything goes as normal, and all of the energy is just transferred a little bit further down the line. In the other case, there's an obstruction, and in fact you have the meeting of two things which are both two-dimensional at this point, that they've got very little substance to them. All they are is a trajectory, but as soon as we see that one trajectory is obscured by another, whilst these trajectories, they don't know anything about each other, they don't hold any information about themselves, they just are along a trajectory. We've got to model those paths as being like dimensionally independent, that one doesn't tell you about the other, but once they meet, you know that they need to be within like the smallest space that contains both of those dimensions. So if you started out with points that just fly out in any dimensions, arbitrary dimensions, and then they ever hit each other, then you would take these two very like point-like trajectories, or linear trajectories, I think point-like trajectories to start. They bump on top of each other, and then you've got a thing which has a location in two dimensions at once, which nothing before had. They were all just going out through these arbitrary dimensions. It seems like also if you meet two things meeting each other in arbitrary dimension land, like it's always the same two-dimensional space that can categorize them, or at least we always see things from the same two-dimensional space categorizing these two little point-like things. As soon as they intersect, we've got a thing that has substance within two independent dimensions, and that's kind of what we need to at least begin on matter. If we imagine that these things were lines with points on them, then we'd have four dimensions, which is exactly what we need for this kind of space, where everything I measure with respect to four dimensions. I measure when it is and also where it is. So we need that to create matter, and we've got most of that from our light computer. There's some interesting things that we haven't really considered about the light computer, which is, well, what is this? I've got an emitter at point 0, I've got a potential blocker at 1 Planck away from it, and then I've got one potential receiver that's another Planck farther. And I'm saying if I shoot and I find an obstruction, I can find out about that within an amount of time that's proportionate to the square of the distance. So if I want to traverse that, I'm sort of talking about the speed of c squared. And if I hit into some of the, I mean, if I hit into anything that's at least an analog for matter, where the energy doesn't just go straight on, it recourses, or it goes back across the same track that it had been, and there's ground that's been more carved in with energy and movement than somewhere else. And also two things going in completely opposite directions, which confirm each other, that they're both exactly the same shape. And so if you ever wanted to see something spinning, this would be a good opportunity to maybe see something spinning. When I go 3 steps away, it takes 6, and the extra weight, the extra delay, is the square of the extra distance. That extra delay, what is it? I'm thinking about light that well, we know if we've got one Planck, it's not matter, right? Yeah. That's a really weird way to think of it, but if we've got one Planck, that's not big enough to have as many dimensions as we need. Because a Planck is the thing that can perfectly fit into one Planck of length or one Planck of time. Does it constitute both at the same time from any frame? Well, so from another frame, where we saw an obstruction could be where we saw something go straight through. I don't think that's what we're looking for. my little light computer. I emit, I check, I potentially receive. What can you do with, just 3 planks? Or just 3 points? All we can do is either send light through or not send light through. And in each case, for light to reach its destination, or to go out, hit the obstructy thing, and then come back in the exactly two length scenario, those 2 cases are going to stay the same. At the smallest resolution there is in space, the amount of energy it takes to keep moving on or to return back is the same amount of energy. Even though if it returned back, we would see over the same piece of space like 2 new pieces of information on top of each other, 2 different trajectories, and the potential to be able to measure this thing in a different way. And if it keeps on going on, we've got 2 planks next to each other. It took the same amount of time, and instead of getting this thing which is potentially a solid, we've got a path through space that takes 2 planks to traverse 2 planks. It does take 2 planks to traverse 2 planks, so that we can't say that the plank constitutes a distance and a duration at the very same time, right? I think we can say that, and then also we're just going to have to take into account that sometimes there's such thing as a hyperplank, like at the beginning of the universe, you've got the first ever thing. It's got to be both space and time, and it's also indivisible. And so then as soon as it happens, there's things around it who all disagree on whether they saw an event or a thing, whether they saw a movement or a direction for movement, whether they saw a movement or a potential movement, whether they saw a movement or the converse of a movement, that everything around a movement that would be pointing and saying, hey, go over here, which is time. No, you can analyze it either way. You can see that the time is running between the space, where the space is running between the time. And so with this really small detail, which one is the obstruct and which one is the pass on through doesn't really exist. But if you have a whole load of obstructs of the same kind, then you've got information that can interact with each other and build up, and so you can put those on top of each other. Now, what's the interesting thing about the c-squared light computer? You go out, you can obstruct it, the distance we get the same function no matter which one we're... Okay, so we've got this light computer and it emits from here. This is a Planck length away. This can either be up or down. If it's up, we get 1 Planck length, 1 Planck length. After 2 Planck lengths, this thing knows that it's next to an object or an obstruction. The other case is it cannot obstruct, and after 2 Planck lengths, this can get the information that the energy, the movement transferred all the way to here. It does that in exactly 2 Planck lengths, the amount of time and the amount of work it would take to traverse this or this. And it just depends on whether there's a guy in the middle. And then we mentioned that if we made this, the receiver, now 2 Planck lengths, so we've got 1 Planck length, 2 Planck lengths, the whole journey takes 3 Planck lengths, 6. And the extra time that it takes now to see that maybe there was something that happened over here, if you want to wait for everything to bounce back, this gap grows at the square of the gap. But you can also move this one. I haven't explained this very well at all. You could also make the system like 3 Planck lengths long, but then the obstructor or non-obstructor is 2 Planck lengths after the emitter. That's going to change like how different it is to see an obstruction or to see a non-obstruction, how different it is to see energy conserved or obstructed along a certain vector. You can tweak how different that seems, and at one end of that spectrum it's obviously going to be that you have matter, and the other end you're going to have energy. So how do we figure that out? Well, we're imagining that energy is the non-obstructive case. And so the extreme of that is where the obstructor is as close as possible to you or not. No, as far away, because you want it to look the same as if it had just kept on going. So if I'm looking at the case that just this computer seems to describe energy, um, I want to put my obstructor as close to the receiver as possible, and then whether or not it obstructs just looks very similar. This is good. It looks very similar to whether it doesn't obstruct. And in the case of energy where everything's trying to move in the same direction, that's what we're describing and what we're looking for. If we bring it way closer, the obstructor, then we find out really quickly and easily that it's an object with mass, it's something that obstructs. So what have we just described? That sounds great. It seems like if you were trying to keep track of everything in the universe, you'd want some things to keep track of those. We identified them as being light waves. They can only exist on light waves. We've really narrowed down where these types of forms would exist, if they do exist, where this check would happen, if it would happen, but where, why, what? We can imagine points of light just by themselves propagating in an empty chamber of however many dimensions we need. They all float around. Sometimes they obstruct because they've all got different paths, and the amount of paths through the space has to be more than the points. So sometimes paths do intersect at points, is given to us from logic. If things are allowed to traverse paths, you don't need anything more than that. Then paths are going to intersect at points. Paths intersect at points. We've got two things which were traversing dimensions which we had to call independent, meeting at a certain point. So now we've got a certain point that we can at least reference by two different locations. And we've got the type of thing that it's interacting with two dimensions, so that if there was any force from something else on either of those dimensions that interacted with it, it would be able to interact with both. If there were any fundamentals, if there were any like harmonics that stay the same throughout all dimensions, certain relations, that there's always something interesting at 6, or anything like that, then it would have been visible to these objects when they were just in one dimension, but then when they strike and hit 2 dimensions, you would be able to see that effect take place as though from 2 different sources, or you would see the square of the effect, you would see it stronger there, because it's a feature of both of the dimensions that were there. And this strong signal that you can find is one of these things that you can find out if you're acting in multiple dimensions at once, which you can't find from any of the ones individually. If we're keeping track of information at all times and saying, okay, well, Mass can change into energy, but complexity has to stay the same going in and out. Total amount of how many shapes are there, that needs to stay the same, or else where did you get those shapes from? Some kind of function, some kinds of interactions are going to be able to sublimate shapes that if I fill up a whole circle with all of the ways that it could possibly shake in, then I need a new dimension for that. Um, so where is this light computer? It seems so neat that there would be one of these that checks for obstructions and sort of can see energy and matter along the same spectrum with the moving obstructy thing. That's great. Now where does it happen? Well, we've said we can imagine light propagating around a vacuum, and there it would happen. That if you have things charting out paths in a place of points, there are more paths than points, so you need to bump into each other sometime, paths upon points. You would have points that have more information about them. What we don't have here is necessarily a way for the electron to get surrounded in light and lose track of time like we kind of wanted. It can be that the points which are sort of allocated as now having more than one history at once, having more than one way of describe them, it can be that these then constitute the points of a next plane up, and that we never see anything where 2 points haven't connected together and made a point that's visible and manifest in a couple of different dimensions. These don't have to be the dimensions that we interact with. These can be still like the space between electrons, but the important thing is that the path that a charge between electrons would make would need to only ever traverse the points potentially that have been already an interaction. That maybe an electron is a feature of these points interacting with each other, and so when you have two of those electrons, which are both features of those points interacting with each other, at least everything that's visible to us is going to happen on those points which have been spelled out by previous level interactions. And it can be that all of the stuff that we care about within that point, within that plane, within that volume of electrons, is where it was the special weirdo points that happened in the volume that was just completely filled with light. That would maybe help us to arrive at the scenario where an electron had been completely surrounded by light, so that in any direction it looks in, it doesn't know what time it is, and that leaves it as spinning throughout its world, because to be any rotation seemed the same as that. That's hard to imagine if light is just propagating around a space and taking all the routes it can take. Why would it ever go into such a tiny curl? But if everything that light is doing from the perspective that we care about happens at those points where things have interacted, then it becomes a lot easier to imagine that there's going to be one point that becomes filled in within that universe, and then eventually all of the points surrounding it become filled in that universe. And that would give us the thing we needed that looked like a point being completely surrounded by the tightest curl of light you could imagine, but instead it's just there's a point there, and all the surrounding points got filled in like that instead of like that. That's good. I like that. That seems a pretty way that you could make. So that would be Young Mills. If I'm anywhere near to it. This is so odd that like the only imperative I have at this moment. There's no way I can help myself in any way except potentially by finishing up this sciencey maths odyssey that I've nearly killed myself in order to come to. But I haven't done it on purpose, just everything around me has become less and less viable. I've got fewer and fewer options to save myself other than keep on sciencing. Uh, and because the just the potential of perhaps sharing any of my things that I've gotten correct, if that exists, is just so much greater than the potential of trying anything else. Uh, well, at this moment, I'm not very good at eating or doing anything. I'm just completely collapsed into nothing good happens if I don't finish the science theory, which isn't true, and it's not even how I'm thinking, but it's sort of how my body is directed. That a moment of time is a spare moment to think about things. We still haven't really talked about what you could do with that light computer, the the light mill. It seems like you should be able to throw up paradoxes of having too much complexity worked out for only a certain amount of light going in. Your computer can work on a finite or can produce a finite number of operations per light that goes into it, and that's going to be a hard limit and slightly different to the limit at which information can travel, but surely related to it. Is there going to be any difference at all? Well, you need to now consider a whole bundle of, you need to consider an all of information traveling from point to point, and yeah, you're going to bump into pi. Cool. You're going to bump into pi of the speed of light to figure out a limit on complexity. Cool. Well, complexity circumstantiation, that things can't get too complex too quickly at a point. At what point? Wow, it can be the same. It can be the same as how we've just described the electron being formed, that too much complexity for the light mill computer to figure out is just going to be, you're not allowed to get back round in a circle too quickly. And that's the limit. So if anything tried to get round in a circle too quickly, you knew that it couldn't do it. What happens there? Well, it needs to go into a new state. You need to ask the space to do something that has never been done before, and you know that you would find a new thing, and you know that you would find a new thing with minimal dimensions and exactly the ones that you had specified. And if you asked space to process too much complexity at one time, we say that should substantiate matter, that should give you an electron. So now I'm thinking, if this is the case, we're going to measure an electron as a function of the speed of light in a circle. One measurement should relate to the other if the things relate to each other that way. The maximum processing I can get from a light mill computer, what's that? Well, if we imagine that one photon can turn the light mill just by itself, and then we're going to have the fans so that it takes one Planck of time for a new thing to be up there for the photon to hit, and it comes out, and we fire one photon per Planck. It keeps on spinning around. What we can never do is keep track of any petals that we would put in between the petals we already have. right? That would require firing light faster than light can be fired. And so is it that we need to find the minimal feasible light can hit this and turn it in a circle thing? I think that's possible, that you could have, a kind of propeller that if you hit just this end with a piece of light, the extra impetus of having one thing of light is going to spin it around. There's a few different ways you can think about nearly doing it, like a normal Crookes radiometer where you just heat something up and then something expands and then pushes it around. But maybe, photoelectric effect to make the thing lighter at one end is going to help. All sorts of ways. We want to think of what is the smallest one. It's not really a practical let's build it task. It should be that I can expand. I would think that I can, by the intermediate axis thing that we were talking about, it should be that if I make my Ferris wheel bigger or smaller, still can take the same amount of push to, because all the forces are going to be counteracted except for that one little extra push. So we're looking for the kind of system that just takes one little extra push. It doesn't matter how big the rest of it is. In real life, it matters how well oiled the middle bearing is. Which maybe is like a constant of how well oiled space is in a minute. We poke the top with one photon's weight, it can go around a bit. Do we want it to go around the whole thing? No, we don't want it to go around the whole way. We only want it to move by one Planck rotation to then be able to measure, well, is the next one hit? And if all the petals were in obstruct mode and you fire a constant beam, you should expect the thing to spin around. And if you take one of the obstructy petals out, you hope that it either stops at a certain point or potentially keeps going around with its excess momentum that we've just said it won't have. It won't, specifically because we're working in this minimal case where it turns one Planck on the push of one photon. So the fact that it can't keep on being pushed around is what's interesting about this special minimal case. And what else? It means if you've got one missing cavity at all, after a certain amount of time, your machine has to stop. It'd be very random. If you didn't know the starting position of the thing, you wouldn't be able to tell when it would stop. You just know that it's going to stop within a certain frame of time that, again, is related to how long it takes to rotate, like half a circle. If I'm using this to compute anything, well, I know for sure that it's not good enough that if I have one petal missing, the whole thing comes to a rest. I want the system that makes each photon hit here have the machine traverse 2 Planck rotations. Well, that shouldn't be possible. So is that the punchline? We've got this, what? The thing can't compute unless you make it bigger. If we specifically need... Is this the light can't compute by itself? if I want to keep track of two different states of these petals, no matter what they are, I need light to go proportionately to the square of its speed. Proportionally to the square of its speed. If I don't want the case where the light mill stops when it reaches an empty petal, but I want any case where it doesn't, where the thing can keep on spinning when it misses one, and maybe just it takes note that, oh, there was an extra delay because we didn't get that extra momentum, but then finally we did, and you would notice like a wave, like excess of momentum, and then, well, no, under momentum, and then excess momentum. As you missed one of the things, it would slow down, and then as you hit it again, it would speed up a little bit, and then resolve itself as the next one came. Yeah. And if I want the case where the thing keeps on spinning so that I can do any computation at all, I want the case where the one photon hits the petals each, what we're calling 2 Planck rotations, which also seems like it shouldn't be possible because it's one photon. But if we imagined that one photon could potentially turn a thing at all, no, because we're saying the excess energy that was added to the system is just one photon, but then is there a way that it ever wants to fall over? Like keep going? Is it totally balanced there? As long as the rotational forces from here have been fully exhausted to get us from there, is what we're saying. And stuff that's pulling up this way and pulling down this way still wants us to roll over. Let's do the thing about squares again. But if I want the minimal system that can spin, that has 2 different kinds of spin, I want each photon hitting my apparatus to spin my apparatus by 2 Planck rotations. 2 Planck rotations is going to be similar to the little thing we set up. And we said that if there's one obstruction, yeah, cool, it takes 2. If there's no obstruction, it takes 2 to reach this bit and like inform the system that there has been some kind of movement. Doesn't matter what it means. If we translate that to the light mill and then keep on moving this, what do we have? That if we want to keep track of, more than one variable at a time. Is that the case? If each photon hits the light mill and gives it enough momentum to spin round 3 times, then there are 3 different states of slowness that you can get. Yeah, where you miss out 3 petals in a row. So it's another thing that you can measure or take into account. Okay, so for those different states of slowness, you could be moving different wheels over here that translate a different kind of slowness to a discretely different outcome. We have more on complexity and light that well, if I want to measure 2 variables at the same time, I've got to wait a little bit, and this wait is weight. yeah, if I want to keep track of two Planck points for the sake of argument, two bits of energy and information anywhere, the more of them I need sets an upper limit on a delay. This is close to being great. If I want to keep track of multiple potential events all together, then for the length of those events in sequence, the amount of time it takes to keep track of all of them at once is the square, is proportionate to the square of that distance. Is proportionate to the square of that distance, is that correct? Yeah, the time it takes to notice the difference between an obstruction and a non-obstruction is proportionate to how much we needed this thing to turn. How much we need this thing to turn? Well, surely that's going to be energy, right? Yeah, that's going to be energy. The sequence, how many things we need to keep track of at the same time as a sequence, that's going to be mass. And what did we say there? Factor was the square of the speed of light. Okay. So we got there our own way. You can see why it seems kind of reasonable to just go all in on science to try and get enough money to eat. Everything makes less sense than science, except logic, which no one wants to hear about. Did we really do that? Did we really just make a proof of E equals mc squared based around a little measurable thought experiment? Yeah, but we've got this one factor that we didn't really narrow down all that much, which is I can tell the difference between energy and matter on a spectrum of how far or close this obstruction is to me. This obstruction thing currently exists like as an analog for a thing that we haven't identified. What is this obstruction? Does it matter? Is it just any kind of obstruction? And we've talked in detail about one of the kinds of obstruction it can be, where the thing is coupled into a couple of different dimensions. But we don't usually think of the difference between energy and matter being, well, there's this thing in the way that obstructs, but yeah, we do. Matter is the thing that obstructs. Okay, so clever clocks try and derive E equals mc squared. Some people even say that it's not E equals mc squared, it's got some fudging constants, but it's E equals mc squared. We're not going to get more simple than E equals mc squared. So that's the truth, because the guess can't be more simple than the truth. Nature does it the most perfectly. This is like the one thing that I'm trusting from former science, that E in fact does equal mc squared. What was our condition about that? I don't know. I don't want to regurgitate it all, but energy was how much the photon needs to affect it in terms of how many things it needs to go through, and we're dealing all with integers, and it has to be the square of, well, the square of the distance that makes. No, the square of. I sound so confident. Okay, there we go. Peace. Bye.